Hey everyone! So today we are starting a new subtopic of the chemical equilibrium, which is acid-base indicators. Because acid bases also establish their own equilibria. We have three theories to understand them. The first is the Arrhenius theory, the second is the Bronsted theory, and the third is the Lewis theory. They try to explain alkalis or bases and acids using the ideas of electrons or protons. Arrhenius said that acids will dissociate in water to release or to give out H plus ions, and the alkalis or the bases would dissociate to give OH minus ions. But there are so many bases which do not have OH in them. For example, ammonia doesn't have OH. So Bronsted said that acids are any substances which donate H plus ions, or you can say a proton, while the bases will accept the proton even if they do not have the OH. Lewis' theory is the most encompassing theory. It said acids are any substances which accept electron pair, and bases are something which donate electron pair. In your syllabus, the most relevant is going to be the Bronsted-Lowry theory. Imagine you had a beaker of water and you're adding aqueous HCl in it. So it's already aqueous, but I'm dissolving it in more water. So now what happens is the aqueous HCl will dissociate into the aqueous hydrogen ions and the chloride ions. By the way, hydrogen ions are also called protons because they literally have only a proton and no neutron. If we look at the water on a molecular or atomic level, you will see that there are water molecules already there, and the HCl was recently introduced. The water molecule and the HCl have their own interaction. What happens is that oxygen donates an electron pair to the hydrogen atom within HCl. The oxygen tries to accept H plus and Cl tries to donate it. The water will convert into H3O plus and the Cl will be left as a chloride ion. Oxygen atom donates a lone pair, or you can say electron pair, that is a dative bond, and at the same time it accepts the proton. By the way, I'm recalling again, a proton is hydrogen ion, nothing else. So the water becomes the hydronium ion. Let me write that. Water becomes the H3O plus, which is known as the hydronium, or you can also call it the hydroxonium ion, while the chloride is left as a negative ion without its H plus. That leads us to another discussion known as the conjugate acid base pairs. Now, what is that? For that, we need to recall our equation where HCl was reacting with water. Water was acting as a lone pair donor while HCl was the proton donor. So HCl was donating the proton, so it was the Bronsted-Lowry acid. While water molecule were accepting the proton, remember? So they were the proton acceptor, or you can say Bronsted-Lowry base. When the water accepts the lone pair, it becomes H3O plus and Cl minus is left. These two are the products. Notice that in the H3O plus you have extra proton and chloride has no proton. So chloride, since it has no proton, it can try to accept a proton again. That is why it acts as a Bronsted-Lowry base. HCl was an acid, but Cl minus is a base, while H3O plus has an extra proton which it can donate, and that is why it acts as a Bronsted-Lowry acid. So a base makes a conjugate acid, acid makes a conjugate base. Like HCl was an acid, but chloride is a conjugate base. In a very similar way, water was the Bronsted-Lowry base, but the product of water, which is the H3O plus ion, it acts as a conjugate acid. So the base makes conjugate acids and acids make conjugate base. To recall more example, we can see ethanoic acid, which is a very weak acid. When ethanoic acid reacts with a base, let's say for example ammonia is working as a base here. So what happens is that ammonia tries to accept the proton from the acid by donating its electron pair, and the weak ethanoic acid will donate its proton. Ammonium ion is your first product made by the ammonia, and the second product, so let's recall while again that ammonia was the weak base, and while the other product you have is the ethanoate ion, which is the ethanoic acid left after donating proton. Ethanoic acid was a weak acid, and the ethanoate ion should be a conjugate base, because acids after donating their proton become conjugate bases, while ammonia, which was a weak base, makes conjugate acid. So ammonium ion is conjugate acid. So always remember, ammonia is basic, but ammonium ion is acidic. While moving on, let's do a practice where we have various chemicals and whether they're strong or weak, and we will identify their conjugate pair. Like sulfuric acid is H2SO4. We know that it is a strong diprotic acid. When it goes in water and donates the protons, we are left with sulfate SO4 minus 2 ion. Sulfate should be a conjugate base. So sulfuric acid was a strong acid, but sulfate is a weak conjugate base. What makes us think that? That is because sulfuric acid dissociates fully, so it's 100% dissociated. And that means that sulfate ion dissolves in water but does not move backwards. So sulfate ion does not move backwards. For the time being, it's safe to say that sulfuric acid is a strong acid and sulfate is a weak conjugate base. We will do more examples to analyze that. Let's say the next one is butanoic acid, which is a carboxylic acid. We know butanoic acid should be a weak acid, but still it will donate the proton. So we get the C3H7CO2 minus, which is the butanoate ion. Butanoate ion should be a strong conjugate base. So weak acids give you strong conjugate base, and strong acids give you weak conjugate base. Like sodium hydroxide is a strong base, and when it accepts a proton you get water. So water should be weak, but it should be a conjugate acid. So strong base will give you a weak and conjugate acid. It's exactly opposite. Ammonia is a weak base, so when it accepts a proton, ammonium ion is made. Ammonium ion should be strong and it should be a conjugate acid. In the next example, you can see H2PO4 minus. It has electron pair on it, so it will accept protons. So it is a proton acceptor. Proton acceptors are bases. So what should be the conjugate pair? The conjugate pair would be an acid. So phosphoric acid is the best example. So H2PO4 accepts protons, while the phosphoric acid will donate protons. So that is why they make a good pair. In the next example, you can see, let me set it, C6H5O minus is also a base because of the negative charge. So it will also accept protons because the protons will be attracted to the electron pair. So it should have a conjugate acid, which is C6H5OH. So that is how we find out that the acids have conjugate base pairs simply. Moving on, now we'll quickly recall acid-base titration. So imagine you have a conical flask with 25 centimeter cube of HCl, which has hydrogen ions in it, and you have a burette which has 0.0100 mole per decimeter cube sodium hydroxide within it. It has the OH ions, right? So now I'm going to draw a graph with the volume of alkali added on the x-axis and the pH on the y-axis. So volume of sodium hydroxide added in centimeter cube on the x-axis and the pH on the y-axis. Before that, I'm going to be adding 2 to 3 drops of the phenolphthalein indicator, which has a pink color at a pH of above 8.2, and it is colorless at pHs below 8.2. So your conical flask will show a color change. In the beginning, when no alkali was added, so obviously it was colorless because it has a pH of around 2 because of the acid. But as you see the burette volume decreases, the pH slightly increases, and suddenly it increases really sharply, and then it becomes stable around 12ish. You can see that at pH 7 you were using 25 centimeter cube of volume, and also at the color change point you were at 25. So the volume at equivalent point when the titration was complete and the volume at color change both are 25. So that is really interesting for us. There is a negligible difference between the equivalent point volume and the color change volume. So this indicator is really good. You can call it a good boy. I don't know why I'm saying that. So let's have a comparative analysis right now. Let's say you have a very dilute HCl solution on one side and an equally concentrated volume of a weak acid, let's say ethanoic acid. In both scenarios, I'm going to be adding sodium hydroxide, so I am drawing two graphs here. As I add 2 to 3 drops of methyl orange indicator here or phenolphthalein indicator here, both will have their own color changes. For example, methyl orange has a different color range and phenolphthalein has a different one. You can see their color ranges on the graph. For phenolphthalein, the main pH is around 8. For methyl orange, it's a big range. HCl starts the titration with a pH of 2 because HCl is a strong acid. But the ethanoic acid starts around pH 3.5 because it's a weak acid. Let's say I know where the titration will be complete. So HCl follows a graph like this, and then it becomes stable around 12 because of the strong alkali. You can see that when the pH was 7 and the titration was complete, the volume is equal to the volume at color change. So the volume at color change when it becomes pink and the volume at the equivalent point is both exactly the same. But for the weak acid, you can see the titration looks like this. And it is very clear that when the color change is happening and when the equivalent points are happening, both are different. When the graph reaches the yellow region, that is very different from the graph reaching pH of 7. In HCl, the volume at equivalent point and the color change are almost same. So phenolphthalein was a good indicator. But in weak acid, you can see the volume at the equivalent point and the volume at color change are quite different. You will see the color change first and then you will see the equivalent point. So that is problem. So an indicator should yield color change. For an indicator, the color change should happen at the sharp change of pH. For a good indicator, the sharp change should have the color change. It should not be very early or very late. For example, in HCl and phenolphthalein, it was really cool. So phenolphthalein was a good indicator with strong acid, so it was a good boy. But methyl orange was not so very good because it was not giving me the color change at the sharp change of pH. So we will talk more about it through past paper questions in the next video. Stay tuned guys. Thanks.